So for my video objectives check, I was given this diagram. It has two charges, each of them are 7 nanocoulombs. They're 4 centimeters apart. This one's negative, this one's positive. Also on the diagram are 2 points, P and Q. And P and Q are 3 and 2 centimeters respectively away from this positive charge. So for part A, we want to know, is the electric field stronger at P or Q? So we know that it's going to be stronger at Q because, number one, the field lines are closer. These here are the field lines. And also the equipotential lines are closer as well. They start out closer, and as they get farther away, they lengthen. Alright? And that covers EF and F3. For section B, we wanted to calculate the electric field at point P. So we're calculating the electric field at this point here. It's 3 centimeters away from the positive charge and 7 centimeters away from the negative charge. Okay, so this is the equation we're going to use. Electric field equals K, our K constant is right here, times the charge divided by R squared. Alright, so this is the electric field for the positive charge, from P to the positive charge. So then we have our K constant, our charge is 7 nanocoulombs, and our distance is 3 centimeters. And then from P to the negatively charged charge, we have the same stuff except that our R value changes. It's now 7 centimeters. So then, to figure out our total electric field at point P, all we do is add these two together, and once we do that, you can see we get 57,079.36 newtons per coulomb, and the electric field is pointing to the left. So it's also in the direction of the field lines, as you can see right here. Alright, and that covers EF and F2. For section C, we want to know what electric force it experiences. So that's pretty simple. It says also that we have a negative 2.8 nanocoulomb charge placed at point P. So what electric force does that experience? We can use our electric force equation, F equals Q times E. So that's the electric force equals the charge times the electric field. We just calculated the electric field, so we know what that is. And we were given the charge value at point P. So we just plug those in, calculate them out, and we get the electric force equals negative 1.598 newtons. And we know that that is to the right because the point charge at P is negative, and we see that it's a lot closer to this positively charged charge versus the negative charge. Negative and positive attract, so we know that it's going to be drawn towards the positive charge. Also, we see that in our value here, we have a negative. Generally, say this was a positive charge, it would go in the direction of the field lines, and then we wouldn't have gotten the negative, but since we got the negative, we know that it is going opposite the direction of the field lines, so it's going to be going 1.598 newtons to the right. Alright, and that covers EF and F1. Now for section D, we want to know, is the electric potential difference between P and Q positive, negative, or 0? So we know that Q has a higher electric potential because the electric potential decreases as you follow the field lines. So these are the field lines. As you follow them, it decreases. As you can see, P is farther away than Q. So Q is going to have a higher potential, and P is going to have a lower potential. So if you just give those some values, they don't mean anything. All that matters is that the Q value is higher than the P value, so 3 and 1. So then Q minus P, or 3 minus 1, is going to be a positive value. So the answer to section D is positive. Alright, and our last section, E, says that the negative 2.8 nanocoulomb charge moves from point P to point Q. So, does the electric potential energy increase, decrease, or stay the same? And how do you know? So, I figured the easiest way to show how do I know is to just use the values and calculate it out. So, this U is electric potential energy, charge, and then electric potential. Electric potential is also K, Q over R, so then you can just sort of put these two together and you get the electric potential energy equals K times the charge divided by the R, the distance, and then times by the charge. So, that's what we did here. We just ran through all the calculations, started with the electric potential energy at point P, found that out. And there's two equations here because you have to find the electric potential energy due to the positive charge. So this one right here, as well as the negative charge, because they both affect point P. And so then you'll just put those numbers in, add them, and that's your answer. So that's the electric potential energy that the charge at point P experiences. Now, we gotta find what electric potential energy it experiences at point Q. So we run through the calculations, same exact thing. The only thing that's different is this R value. Now it's gonna be a little less because Q is a little closer. So, what we get at point P is negative 3.356 times 10 to the negative 6 newtons, and at point Q we have negative 5.87 times 10 to the negative 6 newtons. So we can see that as the point moves from P to Q, the electric potential energy decreases.